So welcome to Margaret's class on the 26th. I'm David Van Slyke, a math teacher that normally does 20 and 25, sometimes other classes up to 105, and I'm your sub for today. We're going to start by talking about decimal point scoops. This is something that you probably have seen already, and if you have, then bear with me if this is slow-paced review. But I assume that for a bunch of people, this will be helpful to have seen before we move into scientific notation. So there's a pattern we're looking for. If I am multiplying these decimals by 10 or 100 or 1,000, there's a pattern. And if you know the pattern, don't call it out quite yet. If you don't know the pattern, take out a calculator and try these and see what happens with the pattern. I'm going to rewrite them a little bit to note that A is the same as 1.23, oh, I'm sorry, 123.456 times 10. B is the same as that thing times 10 squared, because 10 squared is 10 times 10, which is 100. And C is that thing times 10 cubed, because 10 cubed is 10 times 10 times another 10, which is 1,000. Okay, I have bought us some time. What's happening with A? What's the pattern?
The decimal is moving to the right one place.
The decimal moves to the right one place. Okay, and the next one? Somebody else, not Ryan.
2 places right to right, the decimal.
2 places right, correct. My art is bit poor. And the last one, C?
It would be 3 places, wouldn't it?
It is. So you have probably seen this before, and you've probably memorized something to help you keep track of this. I do want to point out before I keep going that I could put a point here if I wanted, right? Any whole number has a kind of invisible decimal on the far side of the ones column if you really wanted it. So some people may have memorized, count how many zeros you see in that number. And that's how many scoots to go. 1 0, 1 scoot, 2 zeros, 2 scoots, 3 zeros, 3 scoots. Other people may have memorized, look at the exponent on the 1. Whoops, this one is 10 to the 1. This one is 10 to the 2. This one is 10 to the 3. And that tells you how many things to scoot. It's the same thing, because 10 to the 1th has 1 0, 10 squared has 2 zeros, 10 cubed has 3 zeros, 10 to the 4th would be 4 zeros, and so on. So the pattern happens in 3 different places. How many scoots, how many zeros, and what exponent if we were to draw it as an exponent. Everyone with me so far? Okay, if this was math 20, I would spend an equally long time doing the division one, but I'm not. I'm going to just whiz through it very fast. So for this one, it is still true that dividing by 10 is one scoot. Now we go the other direction. We get smaller. If I have a cake and I chop it into 10 pieces, each piece is smaller than the whole cake. Divided by 100 is still 2 scoots, but now we're going, again, making things smaller. If I am going too fast, holler, but hopefully my pace is manageable. And again, we are having an exponent pattern if we wanted it. And the number of scoots and the number of zeros and the exponent are the same pattern in 3 different places. Okay, anyone need to holler and have me talk more before we go on to get complicated? No, okay. So much for easy mode. On hard mode, now we have .1 and .01 and .001. And maybe you've never seen this before, maybe you have. Either way, I'm going to write a little below, just like before. You use your calculator if you need to find out the new pattern. Okay, I've bought you some time. Tell me, what's the pattern for A, B, and C? Let's do A first.
It's 1 decimal place to the left.
1 to the left. Okay, how about for B?
It goes 2 to the left.
And C?
Decimal point moves 3 to the left.
Correct. Okay, excellent work. So it's the same, sort of. And the sort of can be important, so let's talk about it. If I want to write a number, I'm just going to grab some spot here. I could write 0.5 And that's great. If you are sitting next to me at a table working on math, if we were in office hours, I can write just 0.5 and you know what that is. If I'm lecturing, I will write it as 0.5. Saying the 0 point in first doesn't make it better, but it's a little more polite when lecturing to your ears. It gives your brains a chance, a heads up. Decimal coming when I say 0.5 compared to just 0.5. If I was in a court of law writing things down like a stenographer, then I would write this down as 5/10, because the place value column is tenths, and I would say there's 5/10. Just like I would say in a kind of formal setting, if we're at a fancy party, that this is 7/100 instead of 0.07. Everyone okay with my quick review on different names for the same decimals? So the pattern we look at when we're dividing, I'm not sure dividing, when we're multiplying by decimal amounts, powers of 1/10, is that we want to have a 1, a 2, and a 3 like before. 1, 2, and a 3. We get that with the exponents. 1/10 is the same as 1/10 raised to 1. There's only one of it right there. So yay, I have my 1, 2, and 3 if I'm thinking about exponents. I don't have my 1, 2, and 3 when I'm thinking about zeros, unless I'm careful to write the 0 that's optional before the decimal point. If I just wrote this instead as can I cover that up? Sort of. Like that, then you don't have enough zeros to make the pattern happen. So if you are someone that habitually leaves off the 0 in front of a decimal point, that's great. You're probably not a lecturer who needs to give people's ears an extra split second. But for this pattern, you want to say, okay, I actually want to put the zeros back. Everyone with me so far? Something I could tell you, but I'm not, is that if you wanted to continue going on and say we have one last instance, what happens when we are dividing by the powers of 1/10? What happens? Which way do we scoot? But we just really care about the fact that when we multiply, multiplying by powers of 10, make it go to the right, and multiplying by the powers of 1/10, make it go to the left. Okay, ta-da, that's sort of part one of what we're doing today. Let me go back real quick to make sure I am not getting in my things. While we're talking about decimal places, I do want to do a rounding puzzle just because you think you are smart. So somebody tried to round our red number, and they normally did it okay, but one of these they made a mistake. They tried to round it to thousandths, and they got this answer. Then they tried to round our original number to hundredths and got that answer, and so on. One of these is wrong. Who can find it? If you find it, don't shout out and spoil it for everyone, but put your thumb up in the Zoom reaction time. If it's not obvious, let's just check them. Did the thousandths round correctly? Should the 6 have changed into a 7? Yes, this 9 is 5 or more. The 6 changes to a 7. That one's good. How about the hundredths? Should this 4 have changed into a 5? Yes, the 6 is 5 or more. The 4 goes up. Is it? I don't know if it's Andrea. Is that how I say your name? I just
It's
got it. Okay.
my first and last name. I was looking at this and sometimes I just miss things, especially in math. Like I'll just completely skip over things. But whereas like at the hundredths, where it's a 3.5, it's supposed to round up to the 0.4 instead of the 0.3. So
So
yeah,
this 3 stays a 3.
it does.
Yep, this 4 is not 5 or more.
But what about, oh, so it's not, okay.
You don't base it on a partially rounded thing. You base it
I
on the
thought-
original one.
Okay, this is where I get confused. I thought this was like rounding in steps.
No, I'm sorry. That was me explaining. It's not that the person
Oh, okay.
rounded step by step, but they took the original number and rounded it several times.
Okay, then I'm not sure I understand.
Okay, well, we just checked the 3 is fine. Is the 8
Okay.
fine? Yes, this 3 is small. It's not 5 or more, so the 8 stays the same. Is this 8 good? Yes, this is it. This 8 is 5 or more, so the 7 goes up and becomes an 8. Is the 5 correct? Yes, the 7 is 5 or more, so this 4 changes to be a 5. Is this 1 correct? No, Candy's putting her hands up like a big X. This 4 is small, so we should round down to 0. This number is closer to 0 than 1,000. It's slightly below the halfway point if we're marching to 1,000 starting on 0. So the thousands was the one that's the error. That should be 0, not 1,000. Almost no one gets this, by the way. Don't feel bad if you didn't. Okay, but I now know you know how to round, and you are affirmed that you know how to round. I'm wondering, how much rounding should we do? So if I take the division sentence, come on, ding. Why isn't that going? I will just try pasting the next one. We can erase that one's working. If I do 40 divided by 7, I get this long decimal. Most of these digits are garbage. That's just, you don't use the Desmos calculator. I'll leave that out. I don't really necessarily have all of this amount of decimal accuracy. Let's think of 3 different stories. The first one, I'm planning my kid's birthday party. There's 6 guests and my kids, so that makes 7 kids. So I need 7 party favor bags. I have 40 pieces of candy. How many pieces should I put in each bag? If I do 40 divided by 7, I get this answer. Am I going to put 5.714286 pieces of candy in each bag? No, somebody tell me what I'm going to do.
Put 5 pieces.
I'm going to put 5 pieces. That's going to use 5 times 7 is 35 pieces of candy, and then I, as the grown-up, eat all the rest. So in this case, the situation tells me how to round. The whole number matters. The decimal point is not really there. Okay, here's another one. I'm going to do these out of the order I normally do. A carpenter has a 40-inch board and cuts it into 7 equal lengths. How many inches long is each piece? Well, maybe 5 inches, but I think I'm a better carpenter than that. Even with just a normal handsaw, I think I can cut to within 1/10 of an inch pretty well. Maybe some of you are better carpenters than me. Maybe for you, you could even cut to 1/100th of an inch. In my mind, either of these could work. It sort of depends on how skilled I am with a saw. It certainly would seem like I am exaggerating if I put 5.714. I don't think anyone can cut a piece of wood with a saw to the 10ths, 100th, thousandths of an inch. But again, we have a real life situation that's sort of telling me about how much to round. Okay, one more that we're just going to argue about. A pharmacist has a small container and the label just says 40 milligrams. And she needs 7 doses, 1 a day for a week. So how many milligrams will be each dose? What issues are you thinking about as you're wondering what answer to say?
The concentrations of, well, the like how concentrated pharmacists go with their medicines. I hear it's very concentrated.
Yes, it does. Is this like a powder that's 40 milligrams total, or is this a much larger amount of physical material and only the active ingredient is 40 milligrams? We don't really know that.
Like a little bit of liquid that is like 1/10 of a cc or something.
Mhm. We're probably thinking, what equipment does she have? Is she using a balance scale? Is she using an electronic scale? How accurate is her scale? Is she having to use some sort of dropper and liquid measurement kind of thing? So this one is, we're not really sure, right? We don't have enough information. You could say 5-ish. Hopefully it's better than that. You could say about 5.7. That seems pretty reasonable if I have 40 something. When I'm making more piles, I sort of get a little more accuracy just because I'm paying more attention to things. I'm having smaller amounts so I can be a little more detailed. So 5.7 is probably the safest answer. But if someone said 5.7 or 5.714, because they've worked at a pharmacy and their pharmacy had a scale accurate to the thousandths of a milligram, then sure, that's a defensible answer too. Okay, so now we've talked about rounding and sort of what makes rounding reasonable in real life. We're finally going to go to your page here, which I'm going to make bigger. So we're on Unit 2.7 about scientific notation. You've talked about gigatons earlier. And we have exponents like this 10 to the 9th. So that's why we just talked about exponent sum. A gigaton means a billion tons. Giga is just a billion. Have you done metric prefixes and the scooting things around to change from grams to kilograms and so on already? If you haven't, we can do that later, but someone nods yes. Okay. So if you were memorizing something like King Henry does usually drink chocolate milk, you probably didn't have giga in that, but it's just sort of farther along that. A metric ton is 1,000 kilograms. A kilogram is 1,000 grams. And we have weights for a car and a liter of water and a paper clip and so on. But now let's actually do the problems. How many tons are 36 gigatons?
$36 billion.
We could just write this as a kind of sloppy thing. We could say 1 gigaton is 1 billion tons. And wherever we see the word gigaton, we'll just replace billion tons. So we'll take 36 gigatons and say, get rid of that and put in billion tons. And that's an important thing to do with sort of what's happening philosophically. I'm taking one unit and I'm replacing it with another unit that means the same thing. I'm allowed to do that. It's no big deal, but sort of realize what we're doing while we're doing it. Maybe we like writing a whole lot of zeros. So in that case, we could say that 1 gigaton is 1 with 9 zeros. Let's double check that that's right. We have millions, and after millions comes billions. So, okay. And we can do the same replacement that we just did above. We have 36 gigatons. The ones we sort of ignore. And we replaced it before with just the words billion tons. Now we're going to replace it with those 9 zeros. And I'm not quite done. Since it's a word problem, I should label it. It's tons over there, and so it's tons over here. This is easy, but the philosophy of what's happening, we're taking one thing and replacing it with something that's equivalent is something that we're going to do in a more careful way later on in class. So I am writing too much for an easy problem to point that out. Okay, questions so far on anything? Okay, I won't take up a full slide for the rest of these. How many kilograms are in 4 metric tons? So I'll take the 4 metric tons, say, 1 metric ton was 1,000 kilograms. So I keep the 4. And wherever I see metric ton, I'll just replace it with 1,000 kilograms. You could also write it as 4,000 kilograms, if you liked that better than zeros. These are still almost absurdly trivial, but the philosophy is what we're building on right now. Just I can take something and replace it with something that means the same thing. How many grams are in 3 kilograms? Somebody tell me what to do for this one.
Just multiplied 3 by 1,000.
Yeah. I'm pretty much just copying my initial number so that it looks like I'm writing steps, because my math teachers have told me I should write good step-by-step answers. It's not really necessary to recopy the initial number. On the other hand, I'm lying. I am used to writing the initial number because of something that's coming up. So it's not a wasted habit. Okay. What about where you have some other multiplication stuff going on? How many pounds are in a gigaton? The answer is this big thing here. And that's an example of scientific notation. So I'm going to take that and start it on a new slide. We could write 1 gigaton equals 2.20462185 times 10 to the 12th. There was once a disagreement among the mathematicians and the engineers about how to write scientific notation. The mathematicians said, we're multiplying by an exponent, a power of 10. So let's just write that. This looks like the kind of math we did earlier when we went at the beginning of class and we're multiplying by powers of 10 and dividing by powers of 10. It's the same thing. It's just scoot the decimal point to the right as many times as the power of 10. The mathematicians thought this was great. The engineers, on the other hand, said, you mathematicians are silly. You are writing everything by hand. We have to submit all of these typed reports and use calculators. And we are the ones building the calculators, not you silly mathematicians. So we have a shorthand that doesn't involve a superscript, because typewriters hate superscripts, calculators hate superscripts. We will invent a different notation. So this E plus, which sometimes is a capital E, sometimes is a lowercase e, just means times 10 to that exponent. That's the engineer version. E plus 12 means times 10 to the 12th. So your page says that more. We'll round it to 2.2, e plus 12. That's the same as 2.2 times 10 to the 12th. And as we've seen, that just means scoot to the right 12 times. Everyone okay so far? If I wanted to actually do that scoot, I could. Let's see what would happen. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I need one more. So I have to put a 0 here, and then I need to, oh, come on. No, just froze. So I had done the 12 scoots just so you could see. We had to put an extra 0 on the end. And I think we are done with, whoops, now I'm in the wrong page. With that. Oh, okay. What do I want? Any other questions about page 79 in your book? No. Okay, then I will move on. So I'll be your scribe. Somebody call out. 1,000, we can write in words as 1,000. And there's two different things we could do. We can say it's 1 times 10 to the 3. We could say it's 1 and then e plus instead of the other notation. I should also add, we could also just say it's 10 to the 3. We don't really need a 1 times in front, but hey. What's the next row?
1 million.
1 million. And what are ways to write that with similar formats?
1 times 10 to the 6 or 1e plus 6.
Yeah, or just 10. And the last row,
1 billion. One times 10 to 9.
yep. One E plus 9 or 10 to the 9. Okay. You may have noticed that your calculator will very often have a button that says EXP. So let's look at that. I'm just using the Windows 10 calculator to put something on the board, but you probably have a better calculator. So we know that this button is the one that actually does exponents. If I want to do 2 cubed is 8, then I use the X to the Y button. So what's up with this button that says EXP? That button, if I want to say 22,300,000, I can input it as 2.23, and then I do that EXP button. And how many decimal point scoots did I just do? 1, 2, 3, 4, 5, 6, 7. So I would put a 7 there. So that EXP button that maybe up till now in your life has always just been a trap. It is useless. It makes you want to use it for exponents, but that's not what it does. It's for entering the exponent at the end of scientific notation. Somebody should have named it SCI or something like that instead, but oh well. Now I just did something kind of interesting. I had several choices of how to take my red number and write it with some sort of times powers of 10. I could have done 2.23 times 10 to the 7th, right? Because 7 scoots brings me over from this spot. Or, actually, let me write what I just did in yellow. I could have started here instead and said this is 22.3 times 10 to the 6th. Or I could have started here and said that's 223 times 10 to the 5th. These are all the same number. Everyone see why? If I put any of these three in my calculator, it gives me this big thing, 223,000,000. So there is a convention about what to do. And this convention goes back to when we talked about rounding. We get lots of stupid decimal digits that don't belong, especially when we do division, like 40 divided by 7. We'll very often, just because it happens when we're doing arithmetic, get more decimal digits than we actually care about. They are exaggerated accuracy. We don't know things to this degree of certainty. This detail is exaggerated. So the convention is that when you're using scientific notation, have one digit, like a ones place, except it's not the ones place, right? The ones place is over here. But just have one digit and then your decimal point. And what that allows us to do is very quickly at a glance, which in many science situations is important, see how much accuracy we have. When I am looking at this one, I can say we've measured this, it's about 2 decimal points of accuracy, and then a whole bunch of filler. That would be different than if I had 2.2 times 10 to the 7th. In that case, I wouldn't know this 3. That 3 might just be because the calculator put a 3 there, but my answer, I'm going to say, I only know it to 1 decimal point of precision. My equipment is only that accurate, something like that. So that's our convention. We like this one with 1 place value left of the decimal. There is a general rule for rounding. You've probably heard it just with decimals. That's, you keep your original number of decimal places or 1 more. So if I have a problem like well, let's just go back to this one as we have it. No, where did it go? If someone writes on the paper 40 divided by 7, then I could say it's 6 because these have no decimal points after them, so I will do the same. Or I could say it's about 5.7. Everyone knows the wiggly about equal sign. If I wrote it differently, now I'm saying I've measured my original things more carefully. I'm using a better electronic scale at the pharmacy or whatever my situation is. So because I am this accurate to start with, I shouldn't toss that away. I should keep that amount of accuracy. So now I will say, well, maybe it's about 5.7, or maybe it's about 5.71. Because again, when we take a pile of whatever candies and put them in 7 piles, we can pay a little more attention. We can have a little more precision often when we physically divide things up into smaller portions. So this same general rule of rounding works when we are using scientific notation, except there will be something like times 10 to the whatever next to all of these numbers. Let's look at how that works. We actually get to do any math with this? No, we're just writing it. That's boring. Okay. Well, let me do one just so you know what I'm talking about. If we have 32.5 times 10 to the 4th divided by 4.8 times 10 to the 3. You might think I am being needlessly complicated. This is just a decimal point here with 4 scoots, and I am dividing it by a decimal point here with 3 scoots. My red numbers aren't so terribly difficult to write. Why would I ever want to do it in this sort of confusing format? I can just put into my calculator 325,000 divided by whatever we had, 4,800. And get about 67.7. And in an abstract sense, if we're on a math paper, that's true. I might just do it this way. But there's some important information hiding in the scientific notation. These quantities were measured to a 1 decimal point accuracy. Somebody is choosing to write the scientific notation in a funny way to emphasize that. So when I am doing my division, it's the right thing to do to round it to 1. And because of that. It's emphasizing what accuracy I want. Okay, let's go back to what we should be doing. So write each number below in standard notation. I have a 7 and a 6. I'm going to be scooting to the right a bunch. Somebody tell me how to finish.
I had 8 zeros.
Yeah, if I write all 9 scoots, 1, 2, 3, 4, 5, 6, 7, 8, 9, then I will need 8 zeros to fill in the gap. They're sneaking a negative exponent in us. Remember what we did at the very beginning. If we have multiplying, we go to the right. If we have dividing, we go to the left. The negative exponent is saying go to the left. If you played around with this, you would see that. I don't want to talk too much more about it because I don't want to confuse people. But this is saying take our 6.2 and go in the other direction. 1, 2, 3, 4. Go in the negative direction, 4 spots. Since these are word problems, I should probably label them also. Everyone okay with my scoots? If somebody wanted to be an engineer and write this 7.6 E plus 9 or 6.2 E minus 4, now we know why we have a plus here, because it could have been a minus. You'd still be able to do it even with the engineering notation. I'm not hearing yeses or nos. Okay. Number 6. This will be annoying, but we can do it. The whole Earth's atmosphere, here is it written as an engineer with the E plus 18. So what number goes in the box, writing it like a math person?
18.
18, yep. Don't make it harder than it is. Okay, here we go all the way across the board. Help me not lose count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then in all of those little divots, we need to put a 0. Ta-da, okay. Everyone happy with this page? Not sure if we should actually do all these. Okay, I'm gonna move on for now. We can do more of this page if you want, but it's just writing them. You can always watch Paula do them with her excellent videos. Her voice is cuter than mine anyway. And we have a lot to do and it's past 1. Am I supposed to go over the 2.8 homework for you? Give you a heads up
No.
on what's coming up?
I don't believe you are. I think it was 2.7, 2.9, I think.
Okay, there's cards. There's a link to the cards in your to-do list for the week. And there's also a link in the main Moodle thing. You can find it. Okay, our next topic will be dimensional analysis, but just like before, to make sure your background knowledge is thorough, I'm going to start with some other things, assuming that we're in Math 20, but going at this rapid pace. So my first review is 3 methods to solve a proportional rate. Some people, when they were given 2 situations, and we're calling them proportional because they scale together. If I drive 30 miles in an hour, I can drive 60 miles in 2 hours, things like that. Some people love to find unit rates. So my situation is a bug crawls 36 feet in 1.8 minutes. How many feet would it crawl in 12 minutes? So these people will say, let's start by doing 36 divided by 1.8. Get 20. And they've turned this into a unit rate because that's what division does. Just like finding at the grocery store how many servings of ice cream you get per dollar or whatever, right? You take the top divided by bottom of a rate and you get a unit rate out of it. We're not done. If we're doing a unit rate of 20 feet per minute, then we'll take that multiply it by the 12 minutes, and get our answer. Everyone able to follow what I just did? Okay, other people like proportions. After all, we named this kind of situation proportional. And for many people, cross multiplying is like their favorite part of a math class. So these people will set up a proportion. They will start reading the problem. A bug crawls 36 feet in 1.8 minutes. If they are smart, they will stop reading and say, I don't care for the moment. Anything else the problem says, I know how to set this up. If it starts out with feet on top, it has to stay feet on top. And if it has minutes on the bottom, it has to stay minutes on the bottom. Otherwise, I might mix myself up and make a careless mistake. Okay, now I keep reading. How many feet, so that's the thing I don't know, would it crawl in 12 minutes? So the way I like things, by the way, we have superpowers. It doesn't matter if I take one diagonal or the other and write it on one side or the other of the equal sign. If two things are equal, it doesn't matter what I put on the left and what I put on the right. They're equal. So I'm always going to pick the diagonal that has the y and put it on the left. Also, I'm always going to put the y first. Y times something is always the same as the something times y. Multiplication you can flip around. So I can always pick the diagonal with y to go on the left, and I can always pick the y to go first. And that means when I write these proportions as cross multiplying sentences, it's always the format y times something equals a bunch of something. And that consistency helps me go fast. Okay, anyway, y times 1.8 is 36 times 12, 432. I have something stuck onto y with times 1.8, so I'll divide. And I'll get my same answer. Has Margaret given you the warning about the shortcut with proportions? No. Okay, so we just had a proportion. The 1.8. There is a shortcut you might have learned where you take the two values that are opposite each other as numbers and multiply those. And then you take the one that's opposite the y and divide by that one. And then you can just say y is 36 times 12 divided by 1.8. If you've never seen this shortcut before, don't worry about it. If you have seen it, here's a little warning. First, why does it work? Because remember, I can always pick how to set up this equation, which goes on which side, and that the y goes first. So the multiplying is always going to be, in my case, on the right side. And then the next step would be to get y by itself by dividing by the thing stuck on y. The problem is, if you are going into a higher level math class, you might someday get something that looks like this. And then if you cross multiply, you get something that looks like that. And now you have a fork in the road. There's two ways to keep going from here. You could do what's called distributing and take this 1.8 and multiply it by each of the y and the +1 parts. If you don't know what I'm talking about, that's fine, you can tune out. Or we could divide both sides of the equation by 1.8 right away to get the y +1 by itself. If you use this shortcut, what you are doing is always picking one of those two paths. You're always multiplying these two and dividing by the 1.8 without distributing. And sometimes that's the fast way to do these kinds of problems. And other times you're going down a very long path without realizing it, because distributing would make your life a lot easier. So the warning is, if this is like the end of your LCC math career, this is a great shortcut that saves you time. Go ahead, use it, be happy. If you are going into more algebra type math, don't use the shortcut. Write down your steps. That will get you in good habits for the higher level algebra classes.
That's actually very helpful because I learned the bat and ball method, which is that shortcut method that you were talking about. And I've not ever seen a +1, like y +1 kind of situation. So that's really helpful, actually.
Yeah, if we're just doing proportional word problems, we never get anything more complicated up here.
Yeah.
So if this is your extent of math, that's great. Yeah, shortcuts work. But in the future, it can trip you up. So if you're going into algebra, stop using the shortcut if you can. Okay, now we have more ways to do this. So some people liked finding a unit rate. Unit rates make them feel good. Almost everyone in my math classes that has had a career in carpentry or construction or baking likes finding the unit rates first. They're used to working with unit rates. Other people like this method because cross multiplying just makes them feel good. It's like chocolate or something, endorphins, right? There's more ways to do this. And the one that I'm about to teach you is called unit analysis. But I'm not going to actually teach you unit analysis yet. I'm going to show you a method that is terrible and no one ever uses it, but it will help you develop some intuition about why unit analysis works, so that when I do show you unit analysis, it will make sense. So here's a slightly complicated problem. Lucy drove from Eugene to LA. On average, she drives 7 hours a day at 60 miles an hour. Gas costs $3 a gallon. Her old car gets 20 miles per gallon. How much did she spend each day on gasoline? I've thrown out a bunch of information at you, and I've written it as a bunch of English sentences, which is not terribly helpful. I can take this and break apart the rates. We have 4 different rates: 7 hours a day, 60 miles an hour, $3 a gallon, and 20 miles per gallon. We also have sort of a goal. We want one day is how many dollars? Everyone with me so far?
Yes.
So this is a little bit too much. Trying to do it this way, I'm going to confuse myself. I can find a bunch of rates. In fact, it gave me a bunch of rates. So the unit rate people are kind of happy, but I'm not quite sure what to do. And there's more than 2 rates going on. It's not just one situation on the left and the other on the right. So the proportion people are a little bit stuck too. I see a hand. Yes, Ryan.
Can I take a stab at it?
Can I take a stab at it? No, because I want to do it a certain way to help develop people's intuition. And I'm not going to trust that you're going to do it that way. But the next one I put up, you can. So I'm going to make like a chain. I'm starting with one day. And I'm going to use this fish symbol. That means goes with. One day goes with what? Only one of these rates has a day in it.
Those are hours.
One day goes with 7 hours. Okay, now, whoops. I want to keep going. So I've used up this one, it's done. 7 hours goes with, only one more of these that I haven't used has hours in it.
Miles.
Yeah, but this has 1 hour and I'm at 7 hours. So I'm going to say, let's do a times 7 top and bottom. Seven times 6 is 42. So I get 420 miles goes with 7 hours. So 7 hours goes with 420 miles. Everyone with me so far? Okay, I've used that one, we're done. I want to keep going.
What miles goes with gallon?
Ryan goes with the gallons. Again, I don't have 20 miles. I need to adjust this. What am I going to multiply the top and bottom by?
What?
20 miles, 1 gallon. So 1 mile.
21. That gets the 20 miles into being 420 miles. Now I've used up that one. And I have one last one. I'm trying to get from gallons to dollars. Again, I'm going to multiply by a 21 top and bottom, so that the gallons is what I want, the 21 gallons. I guess I can fit that over here. Okay, is everyone okay with what I did on this slide? Is everyone wanting to not do that on homework? This was pretty much a nightmare. I had to keep taking each of these rates as I was using them and unreduce them to make them fit my chain as I went across. So that was really annoying. I had specifically designed this problem, by the way, so the numbers come out nicely. If you do it with just random numbers, make up, just cross out all of these numbers and put something a little different, then you're going to see how this is not a good way to do these problems. So we need a way that does pretty much the same thing, but manageably. So I will show you that. Okay. Unit analysis is one of those things that I don't need that. Okay. I'm going to reformat this 1 moment. Excuse me, Lucy. Is it scrolling? All right, my other window where I am copying from. I want this on that side. Okay, ready to go. I just have to do this. If I try and describe these steps to you without showing it, then it's just going to be a bunch of words through the microphone that will go in one ear and out the other. We have these nice rates. We are still going to use those nice rates, but we're going to use them in a better way because this was terrible. It's also true we still have our goal. Okay, so we're going to start out with our day. The day is what we care about. Or we could start out with $1, because $1 is what we're aiming for. The general habit with unit analysis is they're going to give us something and write it as a fraction. Put it over 1 if you need to. In this case, what I want is I'm looking for dollars per day. So I think I should start with dollars. If I accidentally put dollars in the denominator, I'm going to confuse myself. So let's start with the one that has $3 per gallon. I've used up that one. Now I want dollars per day. Do I have dollars per day? No, I have dollars per gallon. So I'm going to cancel out my gallons. I'm going to write another rate that has gallons and something so that my gallons will cancel. Do I have a convenient rate that will get me today because I want dollars per day? No, I don't. What can I use to get out of gallons?
You can use miles.
Miles. 1 gallon is 20 miles. Okay, I don't have dollars per day. I have to keep going. I'm trying to get rid of miles now. Before I was trying to get rid of gallons, so I did. Now I'm trying to get rid of miles, so I will. I need something with miles on the top so they can cancel. I would love it if I had something with miles and day, because again, my goal is to have dollars per day. But as before, I don't have miles per day.
You have hours.
I have miles per hour. 60 miles is 1 hour. Okay, I'm getting closer. I have hours in the bottom. I don't want hours in the bottom. I want day in the bottom. So let's get rid of hours. Can I go from hours to day?
7 hours a day.
Yes, she drives 7 hours per day. Now I'm multiplying fractions. I know how to multiply fractions. I multiply the top and the bottom separately, right? The only word that's left in my numerator on top is dollars. All the others have canceled off. So 3 times 60 times 7, 1260. 1 times 20 times 1 times 1 is 20. How do I turn my fraction into just a decimal number?
Divide by the denominator.
Yeah, I do top divided by bottom.
60.
And it should be the same answer we got before, 63, right?
63.
Okay, now we need to talk a long time. My first question is, I think I'm cheating. I can't just divide something by 20 because I feel like it. Why am I allowed to put this fraction here, this rate here?
Is that because 1 unit? 1 unit.
What I'm looking for does include a 1, but it's not this one. You'll be able to answer that in a moment. Okay, ignore the fact that maybe I'm cheating. Let's keep going. When I make my cross out marks, notice they each look different. Right? Doubles this way, that way. That's just me. You don't have to do that. But this way, week 10, when I'm studying for the final and I look back at my work, I can figure out what I did. Also, I put some 1s here. You don't have to write the times 1s. Some people do, some people don't. Also, it should be true that all the words are gone except 1 on the top and 1 on the bottom. And that's the kind of thing you were looking for. That's how you know you're done. Because sometimes the problems are annoying and give you extra rates. Red herrings. And lastly, this is very calculator friendly. In general, if I'm multiplying a bunch of things across the top, if I'm multiplying a bunch of things across the bottom, it might not come out into nice numbers, but I don't care. The calculator will do all that. And when I'm doing top divided by bottom, if it's not a nice number, I don't care. The calculator does that division just fine. So this method required us to match things up. We needed to get a 7 hours when we only had an hour. That's why this was such an ugly method. It was not calculator friendly. It didn't leverage the calculator power to help us. Whereas this one, I never had to reduce or unreduce my rates. It was 20 over 1, so I just kept it with a 1 and a 20. The only question was, do I write it right side up or upside down?
But
Okay,
if it
everyone
is
with me so
2,
far?
If it is 2, do you need to make it as 1?
If it is what?
If, for instance, if it is says 2 gallon, 20 miles.
Yep.
So do you need to make it to 1 gallon, 10 miles?
No, if it was a 2 here, I would just put a 2 there.
Ah, okay.
Let's go back and do our snail one. Three. Wrong spot. I purposefully gave you a very complicated problem on this slide so that you would see that sometimes unit analysis just is the best choice. This one we could do 2 other ways. We could do it by finding a unit rate first, and that worked great. We could do it with a proportion, and that worked great. How would it look in unit analysis? So step 1, one of these things isn't a rate often, in this case, 12 minutes. If it's not a fraction, then for step 1, I'm going to make it a fraction by putting it over 1. Then I'm going to write some rates. I want to get out of minutes. And I can go from minutes to feet. So sure, I will do that. Then I'm putting in my numbers. 36 feet, go with 1.8 minutes. Now I'm multiplying across the top. 12 times 36. 432. And the only word that's left on top is feet. On the bottom, 1 times 1.8 is just 1.8. And there's no words left on the bottom. So that was my multiply step. And then I'm out of colors. I'll just use yellow again. Simplify my answer, top divided by bottom. And we got whatever that answer was. 240 feet. Most students, when they first learn unit analysis, think this is the worst of the 3 choices. They would rather do it with a unit rate or with a proportion. And that makes sense because in your personal math history, you've probably done a lot more of proportions and unit rates. But as we saw with my terrible example, if we need to keep going with multiple steps, then the unit analysis gives us that power when the other 2 methods don't. So it's nice to know unit analysis, not because it's what you'll always use. You'll use unit rates and proportions an awful lot, but because it gives you sort of a stronger tool for your toolbox than you had before. Should we do a more complicated one?
Bring it.
How many miles per hour is 200 inches per minute? Well, what I'm starting with is 200 inches per minute. And I'm going to write it smaller. So that's what they gave me. It's already written as a fraction. Now I want to get to miles on top and hours on the bottom. By the way, we're approaching 150. So I just want to point out, I'm not doing the dimensional analysis ones from your page because I want you to have more example problems than this. Paula does a great job looking at the videos. It seems silly for me to record a video doing exactly the same problems as you already have recordings of. So I am giving you slightly different problems. Okay, onward. So we want to somehow change inches into miles and minutes into hours. And notice that the thing stays the same. This is length and this stays length. This is time and this stays time. So that means it's going to work out. Okay, should we fix inches first or minutes first? Doesn't matter.
Let's do minutes.
Minutes, okay. I can't put minutes down here. Why not?
Trying to cross it out, so it's got to be on top.
Yeah, I want one on top to cross out with the one on bottom. Can I go directly from minutes to hours? Because I want hours in the bottom. Sure, I know how many minutes are in an hour. Okay, in a sense, we're halfway done. We fixed the time units. Now we have hours on the bottom like we want. Time to fix the inches. Do I know how many inches are in a mile? Maybe you do. I don't have that one memorized. I know how to go from inches to feet. 1 foot is 12 inches. Okay, we're getting there. I have to keep going. We want miles on top. Can we go from feet to miles?
Yeah.
Yeah, I've memorized that one. 5,280 feet is 1 mile. So now we're happy. We have hours on the bottom and miles on top. Yay. Next, we multiply. On top, we have 200. We have 60 and some ones, and miles is left. It's a terrible line. And on the bottom, 1 times 1 times 12 times 5,280. Well, the ones I don't have to write. 12 times 5,280. And hours was the only thing not crossed out. So what is that? 2 times 6 is 12 with 3 zeros. And 12 times 5,280 gives me 6,360. Then I do my top divided by bottom. Oops. Oh, and I get about, how should I round this? We've talked an awful lot about rounding today. Let's actually put that to use. Is 0.2 miles an hour a good answer?
Works. Yeah.
That works. Could I write 0.19?
Yeah.
I could, that's accurate rounding, but neither of my numbers had any decimal points. So putting 2 decimal points is a little suspicious. On the other hand, inches are tiny compared to miles. So I probably actually have a bunch of accuracy if I'm measuring in inches. Maybe I could even put more decimal places than just 2. I think I'm going to compromise and go with this, but if you wrote more or less, that's defensible. So this is more of a snail than a bicycle. Let's look real quick before we have to go at your actual stuff. See what Paula can read to you. Make sure I've covered everything. So we can perform unit conversions using our instincts or our reasons. I showed you about the unit rate and the proportional method, but there is a tool called dimensional analysis or unit analysis that works. See how they're multiplying across canceling out the grams, canceling out kilograms. Then they happen to have, they did their division in the same step as multiplying, which is a little confusing. The way I would write this, you'd have the 4,350,000 on top and the one with 5 zeros on the bottom, and then do a separate division step. But here we go. Then they give you another one. The moon is traveling at 3,356 feet per second. Let's change it to miles an hour because that's what we normally think about with cars and driving. So could you fill in all of the different things? They're not asking you to solve them yet. They're just asking you to fill in the conversion factors. Then they do another one. They talk about the units, what units we want. Why do we have some crossed out? Now they want you to start putting the numbers in. They give you the units. They're being a little trickier. And then finally, they're asking you to do a problem from scratch. 2 problems from scratch. We had one bit of unfinished business. How come I'm just allowed to multiply by these rates? In this problem, it's much easier to see the answer. Can I just multiply by 60? Doesn't that change the answer?
You mean both up and down multiply 60?
Yes, I'm going to paraphrase what Candy said. 60 minutes is a thing. An hour is the same thing. So this is actually, this rate, 60 minutes per hour, is actually like a fraction whose top and bottom are the same. Any fraction whose top and bottom is the same is just 1. So all of these conversion rates are really just times 1, but not written like times 1. But philosophically, that's what we're allowed to do. I'm just multiplying by 1 several times. 1 mile is 5,280 feet. It's the same thing, top and bottom, so that's 1. Okay, I'm going to stop the recording because it's 1:50. If you have more questions, feel free to stick around. And